Okay, so yesterday we did this multi-level paging, wherein size of 4 MB for the page can be reduced to one page directory which is 4 KB, and then as much as page tables that are necessary as and when we populate the memory, we can take those page tables that are relevant, and the other page tables are which for some addresses which are not used, I may not even have the corresponding page tables, right. And so I could have a dynamically expanding and shrinking page table mechanism which is enabled by this multi-level paging. And now please note that as I told you, the page directory, the page tables are also put on pages. A page directory will fit into one page, each of the page table also will fit into one page, right. And this is perhaps one of the reason why we decided that the page should be 4096 bytes, right, so that we could manage all these affairs there. And in addition, we also saw that the 12 bits, the 12 least significant bits need not be populated, it is all zeros, because every page starts at a 4096 byte boundary. So these 12 bits can be basically used for storing some information, and two important information that we put there, one was the valid bit and another is the dirty bit, okay. We may call it clean bit, okay. So whatever. So there is a logical address. This is actually generated by whom? The compiler. This is added with the segment base. This is done, the OS sets this, architecture adds this, okay. We get an effective address, okay. Now in this effective address, this comprises 32 bits, 10, 10, 12. Now there is CR3 which gives you the physical address of the page directory. This is the page directory. Now I use these 10 bits, I index into this table to get the start address of a page table, okay. This will give me the start address of a page table. To this I use these 10 bits to offset into this, and I get this, I get the page address, to this this is 4096 bytes, so this I add this offset, and this is actually my address of the whatever. So this particular location, this is the way we go with the page translation mechanism. And to get rid of multiple memory accesses, right, what we did in this case of segment base, we had a shadow register. Here we will have another content addressable memory CAM called translation look aside buffer. Translation look aside buffer. I look aside the translation. I do not want to go through this translation. What this will store, for every page address, let me call that 20 bits, right, page address, it will store the, so I can call it as the virtual page address, it will store the physical page address, right. So for every input, for every 32 bit input, for every 20 bit input, actually we are interested, this will store this 20 bit address where the page starts. So I can just go give this 20 bits as input to this, I will get these 20 bits as along with all these extra bits, these security bits, and I can basically take that physical page address, right, So I get this address. So to this I can add these 12 bits and directly go and access. So in one shot I will move out of this, I will get this 20 bits here. But yesterday afternoon you would have seen that in addition to this valid bit and in the dirty bit, we have also stored the privilege levels, right? So as a privilege process, as a process of privilege level 0, I may have access to some pages. If my privilege level is 3, for example, and this page is 0, then I will not be allowed to access this. So I am enforcing a lot of security to the way I can access these pages. So, okay. So in addition to these 12 bits, we will have something like, in addition to these 2 bits, we will have something like the privilege levels stored here. Okay. So I could have privilege levels, and these privilege level can be set to 0, 1, 2 and 3. And as we have seen earlier, the 0 will be the kernel process, the 3 will be the user process. This 1 and 2 can be some middleware. Okay. So a process can be a user process, it can be a kernel process. So I can set some privilege levels at these pages so that I could say that if I set this privilege value level as k, any process with k or less than that, numerically less than that. Please note that 0 is the most powerful, 3 is the least powerful. So any process with privilege level k or less than k can basically access that hierarchy. If I set this as 2 and a 3 level process wants to access any address, right, which passes through these 2, then it will be stopped. So there will be a general protection fault, GPF. You have heard about GPF, right? It is fault number 13 or 12 or 13 in your thing. So there will be a general protection fault that will be given basically because you are trying to violate certain privilege level properties. Okay. So essentially what we are saying is that in segmentation we had privilege levels and we were trying to protect segments. Similarly, the paging mechanism can also be used to ensure protection and security by setting up these privilege levels, right. So we will go do an elaborate discussion on how the 32 bits are organized or how the 12 bits are basically used, and then we will see something more in the next Monday's class. Okay, so I'll go through that in full detail. Okay, now, so typically what the operating system will do is that there is we have to start addressing paging from a security perspective so that we get a better deal of this, better overview of this. The paging mechanism, the page table and the page addresses all will be set by the operating system. And first, before enabling paging, the operating system has to set up these page tables, correct? Right, it has to create this. So the first 2 assignments you have done so far, you have not enabled paging there. You have just, it was just in a protected mode and you have just used segmentation. Now you have been, in the absence of the paging, your virtual address space and your physical address space are same. There is no translation. You generate an effective address. You generate an effective address as we see here, and the same effective address is basically used as a physical address. There is no translation that happens in between. But the moment paging is enabled, then this effective address goes through that translation procedure, right. So there is a very simple way of enabling paging. It is to go and set one particular bit in your CR0 register. Okay. So I think that they would have explained yesterday. So you go and set one particular bit in the CR0 register and your paging automatically gets enabled. Okay. Now, so before enabling that paging, we need to go and do a lot of things. One of the thing is the operating system has to set up this page tables, set up this page directory and the necessary page tables. It has to load it into some part of the memory, and while it is doing, it is basically paging is not enabled at that point. So it is doing with the segmentation there. So when you look at in your virtual address space, where will this page directory, page table, etc. will be stored? It will be stored in a segment which is of privilege level 0. Basically, your kernel will be responsible for setting up these page directory and page tables, right? In other way, when a user process in the 4th assignment, you will be doing what we call as task switching. Sorry, in your 4th assignment, correct? So no, 5th assignment, you will be doing the last assignment. You will be doing task switching, where you will be moving from a privilege level 0 code to a privilege level 3 code. So when you start executing your program, what essentially happens in your architecture? So a shell can be a privilege level 2 or 1 or 0 code. You have this shell, right? So now when you start executing a program on that shell, basically then it switches to a privilege level 3, right? So how do you switch from, say, privilege level 0 to a privilege level 3? So these are some very interesting things that we will study in your 5th assignment. Okay, before that, so let us assume that there is a privilege level 3 task, right? Now the privilege level 3 task cannot go and change this page table. In sense, what we are assuring here is by having this segmentation, we assure that the page table and the page directories are completely maintained by the kernel, and the user process cannot go and tamper with it. If the user process can tamper with it, then all that we are talking about inter-process or intra-process protection, everything will go for a toss. Correct? Right? So to start with, the first part of your assignment would be that the first part of enabling paging will be something like you go to the you have a segment which is privilege level 0. In that privilege level 0 segment, you go and fill up all your page directory entry and your page address entries, page tables, whatever is necessary for you, the operating system has to fill. Then it will go and fill up this CR3 with the starting address, of the page directory. It will fill up the CR3. The instruction that can go and fill up CR3, that is also a privileged instruction. We all know what a privileged instruction is. Yes, right? What is a privileged instruction? It can be executed only when the privilege level is 0. So the kernel is now executing. It sets up the page directory, it sets up the page table that is necessary for that program or that process. Then what it does, it goes and fills up CR3. Okay, it fills up CR3. Now then it goes and enables paging. What do you mean by enabling paging? You go and make that bit 1. So once that is 1, immediately what will happen, the next address you are going to put for fetching an instruction, or the next address you are going to load for fetching data, everything will start moving through, right? Moving through this page translation mechanism. Till then, your effective address was equal to your physical address. The moment I enable this bit, your effective address now will become translated to this physical address. So it starts moving through this translation mechanism. Are you able to follow the procedure, how paging is going to be enabled? Is it clear? Okay. Now let us, but one thing, even after I enable paging, nobody can come and tamper with CR3. If I want to go and play with that paging, first thing is I need to have access to the page directory, page table, etc. But since these are all fixed into a privilege level 0 segment, even at this level, when you even generate an effective address and try to access, at that point itself architecture will stop you. Hey, you are going outside your segment. Even before I go through the translation process, your effective address, you are generating an effective address, and that will be in some segment which is not defined for you. So you cannot even go and access that, you will not even generate, because your segment, when I am a user level process, my data segment and stack segment, code segment, etc. will be pointing to whatever is allocated to me, right? I can't go and access anything outside that data segment or code segment. So that is one first level protection. So I cannot go and touch anything outside of what is allocated to me. The next thing is, okay, can I go and change the CR3 and make a page table internally within the segment that is allocated to me? That also I can't do, because CR3 is a privileged instruction. So I can't go and change the value of CR3, nor could I go and change the page table or page directory, because all are in segments. We basically utilize segmentation here, right? All are in segments which I cannot touch, right? So this is how I can ensure that a user 3 process, it is going to use the page table, but it cannot go and meddle with the entries in the page table. Is it okay? Are you able to follow? Right. Now let us go next step. So let us say I am so there will be one code. So this is very, very important, right. So let me say that there are some instructions which are stored at, let us go with your 0x8000, 8005, like that, right. Now let us say that this is the instruction that is enabling paging. So let me say 8000A or 8051 or something like that. Okay. This is the instruction that is enabling paging. The moment this instruction enabled paging, what will be the PC? What will be the program counter after this instruction gets executed? The program counter will be 8015. Will it come to 8015? What will be the next instruction that is going to be executed? Will it be 8015? Huh? It will be some 8015, till now 8000A was 8000A. Now let us assume the next instruction is 8015. Now the 8015 will be pointing to what? It will go through this entire translation mechanism, okay, and this may give me some right, it may give you something else, okay. So what care should we take? We can't write programs like that, right? After this, the next fellow will be somewhere, I will be in Chennai, next fellow will be in some San Francisco. I can't write programs like this. So what care should we take here? Yeah. So the page in which the instruction that is enabling paging is going to be there, that page should be identically mapped, right. This is one very, very important thing, that this is a very practical point, right. The page which carries the instruction that is going to enable paging should be identically mapped. Now let me say that the virtual address space will be filled, this is filled with OS, there will be something for the OS, all the system calls, all these things will be there for OS. Then there will be some set of locations for the peripherals. We have already seen this in your third semester, right. We have some memory allocated for the peripherals. What is that? What is that called? Memory mapped IO, right. There is some, so we handle the peripherals as if I am handling memory. So some addresses will be registered for this, so those things will be there. So these peripherals are going to be there. Then let me say I have some space allocated for P1, then some space allocated for P2, then some space allocated for P3, and then there are some more empty space. Okay. Now note that when P1 is executing, I could have a paging mechanism, right. I could have a paging mechanism where it will see only this and this, right. Why should P1 see this, P2 and P3? So I could have so I have a page table, right, page directory and page table. So in the page directory I will put pages corresponding to this, I will have valid entries here. So if at all my why do I need the operating system when I am executing a program? Because I may want to do printf, I want to do some system call, I want to do so many things. Why do I need a peripheral? Because I want to do printf on a screen. I want to read and write from a disk, I have to do an fscanf or fprintf. So all these things I need. So as P1, please note this is the basis of how Linux is going to, how Linux has developed, okay. So as a process P1, I need to have access only to this OS plus peripheral and this P1. I don't need access to P2 and P3, okay. So when P1 starts executing, I could have a page directory and a page table setup, okay. I could have an exclusive page directory and page table setup within this memory, within this OS part. So the page table, page directory will be somewhere here, okay, in which only OS and peripheral section and P1 section are exposed. When I switch from P1 to P2, I could have another page directory, something here different, okay, some other spot there, which will expose me this OS and peripheral, but P2 alone. So P1 will not be even exposed. So as a P2, I will not be in a position to access the data and the thing of P1, because in your page directory itself these would be invalidated, those pages. So there will be, so in the page directory, let me say that so if I take a full-fledged page directory in which I have entries, let me say this entry will give to some page table which will point to OS plus peripherals, okay. Now this entry will give to another page table which will point to P1, okay. This will give me another page table which points to P2, right. When I am creating something for P1, I will only make this and this available, and I will go and make this valid bit as 0. I just make this valid bit as 0. So if P1 tries to access this entry, if it is going to generate address which is going to touch anything here, immediately it will give a general protection fault, because it is invalid. It will give me a page fault, right, because it is an invalid page. It will give me a page fault. Now the page fault handler will go and find, hey, why are you going there, right, it can go and catch. Are you able to appreciate this? Now when I go from P1 to P2, when I do a context switch from P1 to P2, I can make this 1, so I will enable this, I will make this 0, so P2 cannot go and look at this, right. You are able to understand this. So I can use one single page directory where I will start as an operating system, I will start playing with the zeros and ones there, right. I will just start playing with zeros and ones there, and I can see that P1 will not touch P2, P2 will not touch P1, right. Are you able to get what I am trying to say? Yes or no?
Can P1 and P2 be in the same page?
It can't be. Oh, I don't allocate the same page for P1 and P2.
But like in our case, like in the lab case, memory segment can be like...
No, but that's not for the single process. No. You are only one program here.
Page length is 4096 bytes wide, right?
No, your data and stack and code are all different segments. They are obviously.
Yeah,
but the code of you and the code of him cannot share the same page. We don't allocate like that. The operating system will not. Operating system is responsible for it. So you are writing a code, he is writing another process. His code and your code will not share that 4096 bytes.
So some, like in one page, if some part gets allocated to one process, that whole page gets wasted.
Yeah, that's called internal fragmentation. We don't do that. So that minimum 4096. So we'll discuss all this, right? That's going to be a very nice. It's an interesting question, and we'll try and answer. Right? Why 4096, right? I have only one answer. There are 3 more answers. None of that. Okay. Now you understand. So I have to just basically play with this valid bit and invalid bit to see that P1 is protected from P2, P2 is protected from P1. Okay. Now that is also not enough, because what will happen is that when P1 is executing, if I just play with this valid bit, then P1 can actually go and find out where P2 is allocated. Are you able to follow? Right? I want to also make that secret. So what will happen is, for when P1 is executing, I will have a, see I will have one page allocated for the page directory alone, the pages will be there. So when P1 is executed, there will be one page directory. So these pages are there, there will be one page directory 1 which will point to this and this. When P2 is allocated, there will be another page directory 2, I will just spend one page for just this paging, page directory 2 which will point to this and this will not point to P1. So for every process I could have one page directory, right, which will point to the relevant pages necessary for that process, and as I shift from one process to another process, I will also change the page directories, because my context switch has to be fast. I move from P1 to P2, then that context switch has to be extremely fast. Already there are a lot of things, when we do the 5th assignment, we will find out that there are a lot of issues in doing that context switching. There are a lot of things that will trouble you, that will make you slow. Context switching in general is a very slow process. So I do not want to add to the latency, but what I am trying to do is, when I am context switching from P1 to P2, I will have two different page directories, the top one for P1 and for P2. So when P1 is executing, the page directory for P1 will be loaded, will be used, so, and that page directory will have entries pointing to those relevant pages for P1 alone. When I move to P2, I will have a page directory exclusively which will point to only those P2, right. Are you able to get this? So I can have a combination, it may not just stop with a page directory plus a set of pages also, I could manage it like that, okay. So now that is why when we move from one process to another process, right, when you look at the context of a process, what is the context of a process? So what is the definition of a context of a process? Context of a process is the information that I need to store so that I restart the process exactly at the point where I left. Okay, this is the answer I wanted. Not register, right? Context of a process is that information that I need to store so that I could restart the process exactly at the point where I stopped it. Right? Now, when we go to the 5th assignment, right, we will now find out that in the context of a task process, we will have this CR3 also, right. So the question now I want you to go, if you are interviewed by AMD or Intel, go and ask why CR3 is there in the context. You ask this question, okay. The reason why CR3 is going to be there is because the CR3 for process 1 and the CR3 for process 2 are different. I will get two different page directories, and reason why I need to have page directories, I can do this, okay. Now are you getting a feel of what we are trying to do, right? Now let us go bit historical about why this, why should I, so the question now is, should I ensure protection through paging or should I ensure protection through segmentation? You are already ensuring some protection at segmentation. Why this two-party authentication here? Why should I go on, keep on, everywhere why should I say security, because it drives you mad, right? So why should I so Linux, if you actually study, I do not know whether you will be going through the XV6 next semester, I will talk to your instructor, I am fine. When you actually look at the basic kernel of Linux, the start, it will give you one segment which is 4 GB in size, okay. There you can read, you can write, you can dance, you can do everything there, okay. So it is one segment, full segment, okay, which is some privilege 3. All the protection, it ensures it through only paging, okay, right. It will give you, so the moment you switch on the system when Linux starts booting, the basic kernel assumes that you have a very large 4 GB segment which is read writable, okay. So it puts one code segment which is 4 GB, it overlaps a data segment on that which is read and writable. So it is execute, read, write, everything one 4 GB segment it will take. all the protection it gets through this paging. So between the point where this thing comes up and by the time this paging comes up, that intermediate duration, there I have a security vulnerability. There I can go and put my rootkit and all these things. You understand? Where I can infect a Linux system, this is one part. I give an open segment which I can do anything with that, so that when I am generating the effective address, please note that in the Intel architecture, in any other modern architecture, I can't enable paging without enabling segmentation, right? Segmentation is by default, right? Why I now say that I will have one very large segment of privilege level 3 which can be read, writable and executable, because I do not want anybody to stop anything at this stage. Right? So if I want to execute, if I want to do anything, that is completely taken care of. The segmentation will not come in the way. Segmentation has left off, let you off, do whatever you want, right. So all the protection mechanism etc., I am getting it through paging, and that is perhaps one of the reason why the context switching need to have different page tables for different paging translation mechanism for a different processes. Okay.